Good afternoon, everyone. Thank you all for joining the Australian Water School today for another informative webinar on sediment transport modelling applications. My name's Tegan Burke. I'm an Associate Principal Engineer and Flooding Technical Lead with BMT based in Brisbane, Australia, and I'll be your chair for today's webinar. We've had over 650 people register today, and you can see that those attendees are coming to us from all over the world today, so thank you all for joining us. So our presenters today are Mark Pennington and Alex Waterhouse. They'll be exploring sediment transport modelling approaches in coastal, estuarine and riverine environments. This webinar builds on the previous sediment transport and morphological modelling webinar from December 2021, so you can find a link to that one on the AWS website later, should you wish to check that out. We'll also have Mitchell Smith and Ian Teakle from BMT moderating the Q&A in the background there, come up on screen. So Mark is with Tonkin & Taylor in New Zealand and is a chartered professional engineer with over 25 years of postgraduate experience in hydrologic and hydraulic investigations and analyses. Alex is a senior coastal engineer with BMT in Brisbane, Australia, and he has over 8 years experience in both numerical modelling studies and traditional coastal engineering projects. So we'll have a look at our poll results, if they're going to come up there. Oh, yep, they popped up for me. So we have mostly people today from government and commercial consulting areas and some from academia as well. And we have a pretty even spread of experience, industry experience as well. For the modelling fields that you have experience in, there's a fair spread there, mostly in flooding and stormwater. And mostly involved in 1D, 2D hydrodynamics there, with some people involved in 3D and wave modelling as well. So we might get on to the presentations then, if Mark would like to. I'll hand over to you.
Thanks. You hear me, panelists? Mr. Nod will make me realise. Thanks for the intro. What I'm going to talk to you today about is making real use of a 2D morphological, morphodynamic model, not just building and running one, but actually using it in what's turned out to be a fairly complex construction project, which we are most of the way through the construction of right now. So just to move on, there are 3 elements of this model use that I'm going to discuss with you. They're the bullet points on the left there. Flood level compliance. So that's making sure that we are not worsening a flood risk to a particular area as a consequence of building some new works. There's some scour design where we use the morphological model for that. And then what I think is quite an interesting element in construction sequencing, recognizing that construction of certain projects can take quite a long time, sometimes years, and Mother Nature moves during that time as well. On screen, you can see just a working diagram showing volumes and dredging and closure bunds and that sort of thing. I'll explain a whole lot more about that as the presentation goes on. So a bit of background, I'm talking here about a small town in New Zealand. It's called Opotiki. It sits at the confluence of 2 rivers. This is the town here. One of the rivers flows from the east and the other from the west. They join together, and then a short distance downstream, they flow out to sea. The river mouth is highly dynamic. The mouth position moves quite often and by quite some distances. That's dependent on river and coastal processes. It's got a very shallow bar at times, quite hazardous for navigation, and has been used for navigation in the past. The town itself, being at the confluence of these 2 rivers, is highly prone to flooding. And it is now protected by flood levees. You'll see in the bottom bullet point, I've crossed out the word stop banks. Please forgive me for this. This is a New Zealanderism where we have stop banks, where I think most of the rest of the world has levees. I will try to use the term levees throughout this presentation, but excuse me, you may see on some of the slides the word stop bank. Just know that that's completely interchangeable with the word levee. And just tolerate that for me if you can. So here's an old aerial of the town itself. It's Waioeka River on the western side and the Otara on the eastern side. We've got two lots of levees, one either side. The urban one protecting the urban area. The river mouth flows out through here. One of the interesting components of the flood protection for this town is both the levees, but also the sand movements at the river mouth. During a big flood, the sand is known to blow out and the mouth widen with time as the sand is washed out. There have been a number of historic studies. This is just some outputs or some little excerpts from those, showing a series of different mouth geometries, if you like. That's a plan view. In cross-section, you can see this figure top right here, showing how with time the cross-section does change, i.e. a mobile, highly mobile bed. There have been attempts in the past, indeed, to design the flood levee system, the flood protection scheme for the town. A fixed bed 1D model was used to estimate crest elevations. That required a downstream boundary condition, and this is this figure on the bottom right here, which shows how discharge increases. Well, as discharge increases, the driving head or the water level difference in that estuarine but increases up to a point when you get to about 1700 cumex, and then you actually see the discharge fall away. I mean, the water level difference fall even though discharge increases. Now that's the river mouth blowing itself open, widening. This relationship, this blue relationship, was what was used in the 1D models to set the crest elevations of the flood levees. And is very relevant to what I'm going to talk to about very shortly. Just to ask you to remember this figure of these cross sections showing a period of time in 2003 when the mouth geometry was actually measured, which is quite rare for us. We don't normally measure these sorts of things. And it included two sort of smallish floods that occurred between the start and the end of the measurement period. So further background, what are we doing? There's a project driver, this town, Opotiki, the one that has the flood protection scheme I've just been talking about. There's a desire to establish it as a mussel processing town. There's a whole lot of future mussel farms planned offshore, and they want a facility to bring mussel barges in onshore for processing in this area. There've been a large number of studies gone on as to the benefits of this, and the project received some central government funding to enable it to get underway. Now, as I mentioned before, the existing river mouth is highly dynamic, quite a shallow bar, bit of an obstacle to navigation. So this project about bringing mussels onshore via barges has involved creation of a new river mouth, construction of 2 training walls, and entering into a dredging regime where we look to maintain and operate a new navigable river mouth for bringing mussel barges ashore. Now, we had an understanding of how the existing mouth used to work in terms of flood protection, blowing out under flood conditions, controlling the flood levels, and in combination with the set of flood levees, was able to offer flood protection to the town. What remained to be confirmed is that when we change that river mouth configuration, we're not going to worsen the flood situation in the town. As I said, the highly mobile sediments here played a vital part in the flood protection, so we needed a sediment mobile type analysis to confirm that the new mouth was going to work okay. We were able to consent, which means get permission for the detailed design and construction of this new river mouth. On this image, the new mouth comes something along this alignment here. There were some conditions of that permission or that consent, and one of them, which I've quoted here, was to not increase the flood level in a 100-year return period flood or a 1% annual exceedance probability event at 3 locations, and these are marked by these stars here. So there was this thinking that if we didn't increase the flood level at any of these 3 locations, the the flood scheme would be able to operate unaffected by the proposed mouth works. So we needed a model. This red outline here is a model domain outline. We selected the two-flow FV, the finite volume engine, to build a model using that software. And the idea was to build, calibrate, validate the model for the existing mouth, and then use that to simulate configurations of a new proposed entrance. The mouth has upstream boundary inflows from both of the rivers, as well as tidal level conditions or sea level conditions downstream. There was an interesting joint probability exercise we considered, where you might not get a 1% event in both rivers or in the sea at the same time. I'm not going to delve into that. I'm focusing more on this presentation on the morphological modeling. So we built a mesh, a terrain mesh. In here, the town is sitting in this sort of area here at the confluence of the two rivers. On the left-hand side, you can see a representation of what the existing river mouth looked like at the time we did the bathymetric survey. As I said, it does change quite a bit with time. And this was one of the configurations we looked at for a new river entrance or river mouth. What you can immediately see is there's a great deal more capacity in this new river mouth. As I said, it was one of the configurations we considered. There's obviously an economic element to this, where you don't want to build excess capacity more than you have to because it costs too much. You want to build just enough so that we can protect the town from flooding, but still achieve the navigability requirements that we're after. Having done that, we needed to collect a whole lot of grain size information, particle size distributions. Each one of these yellow triangles is a test location from which we took samples and tested them. Again, this orangey red outline is our model outline. And you can see we've split this river channel into several discrete zones described by their sediment characteristics. Generally, upstream was more coarse sediments and downstream were finer sediments. The next slide actually shows it a little bit better. So each one of these pie graphs is a sediment composition representative of all the tests carried out in that zone. The purpley colors are for the more coarse grained sediments or boulders, cobbles type sizes, whereas the yellow and even paler yellow are for the finer fractions. We were able to, using two-flow FV, we were able to run the model with all of these sediment fractions present at the different locations. As I said, we split the model into zones. Initially, we had just the grey coloured zones, but we found there to be too rapid a transition from one zone to the next. So we inserted these pinky salmony coloured zones as averages between the upstream and downstream zones, just to smooth that transition a little bit. Obviously, with the new river mouth that we were proposing to construct, we didn't know exactly what the grain sizes were going to be. We had to estimate that based on the PSD samples we had taken. So this is the configuration we came up with. In addition to setting grain sizes in different zones throughout the model domain, we did inject some suspended sediment. I'm not going to dwell on this this slide very long, just to say that we had essentially rating curves for each of the rivers, where there was a relationship between discharge and sediment concentration that we applied as we injected sediment in together with the water flows. As I mentioned before, we had cross sections taken over a period in 2003 that covered two flood events. These are the two. This is the flow record and the tide record over that period of time. So we knew how the cross section changed with time over these events. What we didn't know exactly is where those cross sections were taken. So I've drawn two lines here, vaguely representative of where I thought that original study located the cross sections. These are those cross sections replicated. On the right-hand panels here, I've shown those same two lines, but plotted over different aerials of different points in time. And you can see how much the mouth actually moves with time. What I've shown over the top of these measured cross sections is a modeled cross section from an assumed start bathymetry in our model, running this period of time through these flood events and what it resulted in at the end. And they are the orange and blue lines here. What you can see is the model is giving us a mouth that is roughly representative of what was measured at some time in the past. This is about as good as we had in terms of hard calibration data for the morphological component of the model. Ideally, we would have bathymetric survey immediately before and again immediately after a big flood, and then we could calibrate the model to that. But that kind of information is very seldom available, and indeed, in our case, was not available. And we went back to the best that we really had on record and satisfied ourselves and indeed our peer reviewers that the model was behaving in a manner that was roughly consistent with reality. In terms of flood level compliance, this is a very busy slide and I don't expect you to look at everything here. We were building a 1% probability event. It was a joint probability approach that we took where the 1% flow didn't occur in both rivers or the sea at the same time. And what I've shown here is that using this morphological model, we were able to demonstrate to the consenting authorities' satisfaction that the new river mouth was not going to cause elevated flood levels above what they would have been had we not touched the mouth. And that's what this series of figures shows. What you do see here is I've got a column called manning end roughness and low range, high range. Because the model wasn't in a purist sense properly calibrated, we ran everything as a kind of a sensitivity basis where we looked at an upper and a lower bound and made sure that we were happy with the answers at either upper or lower bound, in which case we were satisfied that the model was giving us results that we could believe. So, as I said, using this morphological model, we constructed it to replicate the pre-development situation. We then simulated the new river mouth and demonstrated through this process that the new mouth opening should not cause elevated flood levels for that 1% AEP flood event in the town. Another use we made of the model was in looking at the scour that was likely to occur. So on the left-hand panel here, I've shown a start bathymetry, recognizing that it moves with time. And then if we ran, it was a 1% flood event, 60-hour simulation time, how much the bed deformed. And on the right-hand panel, it shows the amount by which the bed changed from that start bathymetry over the 60 hours to covering a flood event. What you can see is high degrees of scour through the entrance here. That is the sandbar blowing out, as I described before, offering flood protection to the town. We then ran the same sorts of analyses, but for the new river mouth, a closed existing mouth and the new river channel. Now what you can see is the actual amounts of scour or bed deformation is a bit reduced, but then if you look at our start bathymetry, it's from a very nice dredged channel which has lots and lots of capacity. So that's kind of what you'd expect. What I have to say is this model was not the only tool we used to do scour assessments. It was one of many analyses that we did to satisfy ourselves that the structure we were proposing to construct was going to be durable. But indeed, the model was helpful in getting a good understanding of the likely processes at play. So having, well, a really good use of the model that we made was for these scour assessments, not only around the proposed structure, but looking at would this new structure cause scour to any areas that would not otherwise have been subject to scour. Now, in a highly mobile environment like we have here, it's only a guide, but again, we were able to satisfy ourselves and the consenting authority that the effects of the proposed works were within acceptable bounds, even from the scour point of view. So having consented the works, designed them, we were able to move into a construction phase, and you can see the sequence through here. Given we had an active river mouth, a river channel, which flowed out to the western side of these works, we had access from only one side to construct the two training walls. And you can see how construction progressed here. Ultimately, in June of this year, we had just a thin causeway between the two training walls, with all our access for construction coming from the eastern side, which is sort of the left side as we're facing it here. We're facing roughly sort of southeast in these photographs, which brought us into this very interesting phase of how do we change the river mouth channel direction? How do we tell the river now to flow between the training walls and to stop flowing on its original path? This is where the model really came into its own. So we had multiple fairly frequent bathymetric surveys being redone, because given how long the project took to construct, or has taken to construct, Mother Nature has not remained static over that time. We've had storms, we've had big swells, we've had literal drift, we've had all sorts happen, and we've needed to update our model. It didn't stay nicely the way it was when we first consented it or first conceptualized the whole project. So we needed to look at a large number of options based on what was happening in the real world and what were we proposing to do to the real world, and how do we make sure we protect the upstream town from a disastrous flood event. So what you can see here is we're looking at scenarios of dredging through this area to different depths, -1, -1.5, and -2 meters ARL, while we're looking at different river mouth closure options. What you can see over here on the western training wall here is a large stockpile of sand. We won this sand by dredging the adjacent beach, but also the channel here. And the purpose of this is, once we started opening this river mouth, this whole western breakwater and stockpile became an island, and we couldn't get any more material onto here. And this material then had to be used to form the closure across the existing river mouth. So open here and start closing over here. So that's the kind of thing that we were looking at all the time during the process of opening this side and closing this side. We had to ensure that if we were unlucky enough to get that 1% flood event, could we manage it in such a way that we weren't going to increase the flood risk to the upstream town? So looking at the channel opening sequence, this was a big day, a big week, July this year. There's the thin causeway. You see the big stockpile of material here. This is the new mouth, which hasn't yet been opened. In the afternoon of that day, we started opening it. It progressed, and what you'll see at the time the opening is progressing, and I'll try to show you with the little laser pointers, you can see a little closure bund starting to form here, where we started pushing material to close the existing or the original channel and replace it with the new channel. So what you can see is, over the course of a week, we'd opened up the new channel, hadn't quite closed the existing, and there was a good reason for that, and that was flood protection. Every single time we made a change to this configuration, we were rerunning this morphological model for those 1% AEP flood events, to confirm, to be absolutely certain that if we were unlucky enough to have an event occur, that we weren't going to worsen the flood risk. And as I said before, it all depends on the sand movement, how high the flood levels get in the town. So you can see in this image, we've actually formed that closure across here. The next one I'll show it a little bit closer. While we were still dredging the main channel here, we hadn't at that stage got quite the depth we needed to convey the 1% flood through there. So we had to keep this closure at a sort of an overtopping level, that this would overtop and scour out before the town got flooded out. You can see the dump trucks on site here. You get an idea of the magnitude of the project. The stockpile of sand has gradually been eaten away and fed across the mouth here. And as I said, all the time, and it was probably each week we were running the model for 20 or 30 different scenarios of flood level versus causeway level versus dredged volume coming through here with different bathymetric surveys. A couple more photos, just of different angles as this dredging is progressing. You can see here we were very, very lucky with a great weather window. We had very small swell and very low river flows at the time. We actually kind of wished we had a a bit of a flood come down to help us dredge this channel to scour some of the material out. But we'd rather have had it the way we did than have a disastrous flood when it washed everything away. This is a bit more of a zoomed out. You can see we're forming the closure here a little bit more thoroughly. In the foreground here, you can see a precast yard where we were casting the handbar units used to form these training walls. And you can see we've got a much bigger dredge in place for this right now. What was quite good is in 2014, when we conceptualized the scheme, this was an artist's impression of what the whole thing might look like built. And this was just the other day or a few weeks ago, what it actually looks like. This is a drone photo. This is just an artist's impression. A little bit of convergence there between the two, which is quite satisfying to see. So going back at how have we used this morphological model over time? The starting point was flood level compliance. Looking at that, saying, can we put our hands on our hearts and say we're not going to increase the flood risk to what is quite a flood-prone town through the construction of this new harbour entrance? We've also used it for scour design, and again, just to inform that scour design, what are the scour depths likely to be? Where are the hot points going to come up? And lastly, in the construction sequencing, making that balance between river flow, capacity, dredged volumes, closure amounts, all the time ensuring that we're not increasing the flood risk to the town. Big ups to Tuflo, though they were enormously helpful in us setting up and running this model. We were pushing our own technical limits all the time, and we were very well supported by them. And finally, some acknowledgements to our clients and funders of the scheme who actually made the whole thing happen. Yeah, happy to move on. I think Alex is in the wings, ready to carry on with his presentation. And the way I understand it, I think Tegan is going to run some questions at the end of Alex's presentation. So thanks all for listening. Happy to answer questions, but at the end of the following session.
Well, thanks for that presentation, Mark. That was great. So my name is Alex Waterhouse, and I'm a coastal engineer at BMT. And the project I'm going to talk about is some modelling we've recently done of the Bribie Island breakthrough. So just an agenda, we're going to talk about Bribie Island and the breakthrough. We're going to talk a little about the project and then get straight into the modelling we did, which was really looking at hydrodynamic impacts, and then we're going to focus in on the morphological modelling that we did. But first of all, let's do a high-level summary of why we're all doing this. So Bribie Island, you can see this animation that just started playing here over on the right. In 2022, Bribie Island broke through, and pretty quickly after it broke through, the navigational access to the northern section of this estuary was blocked off by a sand shoal. So you can kind of see it start to form up right about here. And this quickly led to calls from the community to reinstate navigational access. So you can imagine if you had a boat up here, it was now very difficult to get out, and you can no longer also get into this area. So our role was to look at the feasibility of using dredging to reinstate navigation in this area. And we did this using some modeling. So to get everyone located, so we're in Australia, and specifically we're in the state of Queensland, outlined in the green up here. And we're in southeast Queensland, right in the bottom right. You can see here is Moreton Bay and Brisbane City, the state capital, down here in the bottom left. And then there's these 3 sand barrier islands, of which Bribie Island is one of them, just up here outlined in red. So Bribie Island is a detached sand barrier island that's entirely separated from the mainland by an estuary called Pumice-Stone Passage. And interestingly, it has a history of erosion, including both shoreline recession and net southerly longshore transport. Which is interesting because for southeast Queensland, the modal wave climate typically is southeasterly. So you would expect that longshore transport heads to the north. But Bribie Island is afforded some level of protection by the other sand barrier island, Morton Island here, as well as this this shallow sand shoals out the front. Either way, we're going to be focusing on the northern tip of Bribie Island, say where the breakthrough was, which is right up here. So this is zoomed in on what Bribie Island, the northern tip, used to look like, and it's kind of looked so similar to this for the last couple of decades. You can see here Pumice Passage, which is the estuary, and then there's the town of Caloundra up there, and the original entrance is called Caloundra Bar. It's what we're going to refer to today as Caloundra Bar. And more recently, it looks like this. So you can see the breakthrough, the new breakthrough here, has formed a new entrance system. And we're going to be talking about this and calling it Bribie Bar today. So Northern Bribie Island has long shown indications of there being a transition point between the longshore transport. So as we said before, most of Southeast Queensland receives northerly longshore transport, but Bribie Island itself typically has a net southerly transport regime. And this transition point is right about up here where that breakthrough occurred. And this hints that there's been prolonged sand volume loss. And you can see that in the island, how narrow it gets in this section. So leading up to the breakthrough, about a year before it happened, there was a large storm that came on and waves overwashed the island, and sand was lost to the deep tidal channel just behind it. And then a year later, ex-tropical cyclone Seth eroded the dune below the tidal level. And very quickly, tidal action formed a channel, carved it out, and this grew to about 150 meters wide in just days. And then a year on, this is stabilized to be around about 1 kilometer wide, the whole entrance, but it maintains that 150 meter wide deep channel in the north. So Bribie Bar is now a highly dynamic entrance system. And as we said earlier, this large sand shoal has formed across what was the historical north to south navigational route in Pumice Passage, which means that your access is blocked via vessel to get into the northern section or get out of it. And this led to calls from the community to reinstate access. So our client, Maritime Safety Queensland, tasked us with looking at modelling to, first of all, assess what are the impacts hydrodynamically of the breakthrough. So they wanted to understand what's happened to water levels, currents, tidal prism and wave penetration by the breakthrough, and then also look into intervention solutions. And when I talk about intervention solutions, I mean using dredging to reinstate access. So cutting a channel back through so you can get into the northern area. Before I get onto the modelling though, I'd like to talk about some of the data we received, which was instrumental in allowing us to do this modelling in the first place. So the client MSQ, they procured satellite-derived bathymetry. They received a data set both before the breakthrough and 2 data sets after the breakthrough. And these were foundational in letting us do the modelling here in the first place. So even pre-breakthrough, there wasn't a lot of survey to begin with, but as you can imagine, post-breakthrough, there was virtually no survey data around the area, apart from maybe the channel itself. But because this is such a hydrodynamically complex area, you need almost a map of bathymetry. So this satellite-derived bathymetry allowed us to set the model up. And also the fact that they provided us with 2 data sets post-breakthrough allowed us to have a target with our morphological modeling, basically a calibration case. We'll see that soon. So a little bit about the model. We use 2-flow FV for all the modeling here. You can see a zoomed in shot of the mesh on the right-hand side. And we had about a 20-meter resolution of cells in the breakthrough area. And we just kind of covered the cells over everything, including the deep areas as well as on the land. We coupled the model with SWAN because we needed to include longshore current in the model. You can see here on this picture on the left that we have, this is just a picture of significant wave height. And you can see how this transforms in from the SWAN model into the 2-flow model, with the boundary of the 2-flow model shown in red. Other key configurations of the model were that we had to use variable bed frictions because Pumice Stone Passage itself is quite complex with muddy flats and mangroves and such. And the model is run in second order, which is a 2D model. And for reference, when we talk about the simulations, all the hydrodynamic impacts were done just using a 1 month long simulation, and the morphological simulations were covering about 6 months. So getting straight into some of the interesting results. First, looking at hydrodynamics. So there was a notable increase in tidal range post-breakthrough. We'll start with the image on the bottom left, which is a time series picture that shows the water level of a typical spring cycle, both pre-breakthrough in blue and post-breakthrough in the orange. And what you can immediately see is that there's been an increase in the order of 40 to 55%, or 0.4 to 0.5 meters. This station here, coincidentally, was where we did our validation as well. So you can see that station is a real recorded station where that star has popped up. So the map on the right, this shows this change in water level range spatially. So in this case, the colors represent the 95th percentile tidal range. And you can see that in red indicates a larger tidal range and blue is a lower tidal range. And pre-breakthrough, the tide signal was very attenuated coming into Pumice Stone Passage. So parts of Pumice Stone Passage received significantly lower tidal range than the open coast. Whereas post-breakthrough, this has changed. And now parts of Pumice Stone Passage are now receiving larger tides that they never had to deal with earlier. So this is a little animation of a 24-hour spring tidal cycle. So on the left-hand side again, we have the pre-breakthrough and the post-breakthrough on the right. And the colors represent current speed and the arrows represent the direction. So there's a few things I want to point out about this animation. First of all, if you notice a caloundra bar, the currents were typically stronger during the ebbing tide in the previous state. But since the post-breakthrough, that ebbing current has significantly reduced, and now the flood tide is actually stronger. So we might say now that the caloundra bar is flood tide dominated. Bribie bar is ebb tide dominated. So the ebbing current is stronger than the flooding current. And this does have important implications in morphological evolution, and we'll see that soon. So getting into the setup of the sediment transport model, we used two flows sediment transport module, and we had it with coupled morphology. Just a little schematic that shows how coupled morphology works. So the hydrodynamics provide the information that the sediment transport module needs to calculate sediment loads and transport rates. And then these transport rates update the bathymetry, which the hydrodynamics consider in the next step. So the sediment transport model that we used was Van Ryn's transport. So this is what we used for our erosion, bed load, and settling model. And we chose to use this based on previous experience with other dynamic mouth entrances around the Sunshine Coast. There are other ones in the sediment transport module that also work here. For example, there's Salisbury Van Ryn or Waioeka. But the transport model provides quite a few adjustable parameters that allow you to fine-tune current and wave-related transport efficiency. For this model, we only considered a single sand fraction that had a median grain diameter of 0.2 mils. It's important to note that you can also model multiple sediment fractions, including silts and gravels in the sediment transport module, but we didn't really need to in this case. So I thought it might be helpful to talk about the sediment transport processes that we need to get right in order to have our morphology work the right way. So starting with the map on the left, we can see in orange what we call our ebb tidal transport, or basically transport due to the outgoing tide. And you can see this ebb shoal here that kind of forms out because of that tidal push outwards. The smaller arrows in blue represent the transport you might get on a flooding tide, and they're a bit smaller because, as we now know, Bribie bar is ebb tide dominated. Also important is the cross-shore wave transport. So during modal wave conditions or typical wave conditions, sediment tends to go onshore, but then during stormy conditions, that balance tips over and the sediment is driven offshore. And then of course we have longshore transport. So depending on which way the waves come into the coast, they will drive transport either up or down. What this might look like in our model is this. So this is a little short animation of just a 24-hour period during quite a stormy wave condition. So there's waves coming from the southeast in this case. So you can see that that's causing this kind of longshore transport going northerly. Other nice things to notice is the ebb currents. So about to see right now that ebbing transport rate really picks up on the tide, and you can see it also across the ebb shoal out the front. Because we've got quite large waves in this short animation, you can see that there is an outgoing direction of sediment. So the sediment is being driven away from the coastline. And of course, there's also the flood current. So during the flooding tide, sediment transport does head inwards. So moving on to talk about the morphological model more and the calibration. So as we said, we had a second satellite-derived bathymetry dataset about a couple of months after the first one. So you can see the two of them here on this left top row is our starting satellite-derived bathymetry dataset, and the second row here shows the one we received a couple of months later. And this is how we validated our model. So we begun our model for that first data set, with that being the basis of our bathymetry. And we wanted to see that we could get our model to capture the key processes shown in the second data set that you can see here on the middle row. And the difference between the first and second satellite-derived bathymetry data sets and our model are shown on the final row. So some key things to point out here that the model did particularly well was capture the ebb shoal growth. So you can see here just offshore, this red area that both the satellite-derived bathy and the model sees. We can see the onshore migration of sand down in here, and also the flood shoal formation. So that's up here at Caloundra Bar, and we can see that it's beginning to close up. The calibration was done quantitatively, but I haven't shown any of the metrics today because it's too many numbers to go through. But these pictures show that things are generally working quite well. So let's look a little bit more about those processes. So this animation here covers about a 6-month period, so a 6-month simulation, and the time step is just every 7 days. On the left-hand side, we can see the absolute bed elevation of the model. In the middle, we can see the instantaneous difference in bed elevation from time step to time step. And on the far right, we see the cumulative difference. And if we go through those key morphological processes again, first up, we can see how this ebb shoal grows. We can also see that there's an onshore migration of sand going in. And we can see the flood shoal forming up at Caloundra Bar, closing the mouth. Now it's probably a good point to note that a lot of the animations and figures in this presentation have been done with the help of our TwoFlow FV Python toolbox, which has got revamped recently. So if you're into Python and you're doing some FV modeling, I recommend you do check it out. Okay, so we'll move on to talk about the modeling we did for the actual scenarios. So we looked at several dredge channel layouts for the client. You can see these along the bottom row. So we had a baseline scenario on the far left where we have no channel. We had a few channels where we had them going through that flood shoal. We had one very large long channel as a what if scenario. And then we also had a combined case to see what would happen if there were 2 dredge channels for whatever reason. If there was a natural breakthrough of this flood shoal, for example. As I said before, the scenarios went for 6 months. And importantly, we also did a sensitivity test where we ran all these scenarios over a different environmental period that had a stronger wave energy climate, just to see what would happen and to make sure that our results aren't being biased just by the environmental period. The results from this showed, interestingly, that constructing a channel, any of these channels through the flood shoal or through these western shoals, increases the rate of infilling at the Caloundra Bar entrance. Also, that any of these constructed channels would have a high risk of infilling, like so you can see in this table down the bottom, that the sedimentation of the original dredge volume in a percent could be up to 50 to 60%. And the time scale of the infilling is measured within weeks to months. So all in all, these results are showing that if you're going to dredge a channel here, it's highly likely to infill very quickly and it will require maintenance. And dredging in particular is very expensive to get plant mobilized. So it's likely to be unfeasible in this case. So to wrap up, Bribie Island breakthrough caused some pretty quick alterations to Pumice Passage. It happened really quickly, as you can see by all these images, this little animation on the right-hand side. And the project that we did was undertaken in late 2022. So we started less than a year after the breakthrough actually happened, and we carried on into early 2023. And during this project, the area continually changed as well. So interestingly, the sand shoal that we're talking about that blocked navigational access naturally broke through at one point, and this has restored navigation in the meantime. This channel is still very dynamic, which kind of confirms what we saw with our morphological model. So the way it looks now is not even necessarily how it first broke through. It's continued to move a little bit, but in the meantime, it addresses the immediate navigational concerns. So thank you very much. I'll leave you with this picture of what it looks like nowadays. So this is Kalanjubar. You can see how it's closed up quite a lot. And over in the distance, you can see Bribie Bar out there. And you can see the beginnings of where that flood shoal has started to break through.
Excellent. Thank you, Alex. That was very interesting. Mark, you're back on as well. Thank you both for your presentations. Very much appreciated. We've had some great questions coming through that Mitch and Ian have been busy answering. So Mitch, if you'd like to bring up some of the ones you've flagged to answer live with Mark and Alex.
Yeah, thanks very much for both your presentations, and thanks Tegan. Please feel free to ask a lot more questions if you have any. We'll be here for another 10 to 15 minutes if you need us to be, and we'll also answer all your questions as a follow-up to this webinar. Mark, I'm going to put you in the firing line first. Just had a few questions that came through to answer live. Tully had a question regarding the sensitivity analysis that you were doing with the flood levels. What were the different factors that you looked at, and how did they affect the model results?
Sure. As with any model, there's a lot of uncertainty. So right at the grassroots level, there was uncertainty in the hydrology, the flows, mainly the timing of flood flows down two different river systems. Did the peaks arrive at the same time? Were they offset in time? Did the flood occur at high tide or low tide? Was it spring tide or neap tide? All of these had effects. An interesting example is if you want the highest flood levels, you'll assume the peak of the flood arrives at high tide. But if you want the greatest scour depths, you'll assume the peak arrives at low tide. So there was no one answer to that. We needed to consider multiple answers. But other factors, just Manning's end roughness, that would have affected it. For the grain size distributions as well, we had an envelope of grain sizes for each zone, and we ran the model at the upper end, around the middle of the range, and at the lower end of the grain sizes to get an idea of the sensitivity. That certainly had an effect. Those are the main ones that I can think of right now, Mitch, to answer that question.
Yeah, thanks for that, Mark. If you do have follow-up questions, feel free to send those through. Okay, Alex, you're up next. I had a question from Philip. What was the source of the satellite images that were used to derive the bathymetry?
So Alkaline procured them for us, but I believe that the source might have been Digital Earth. So it's a fairly high resolution satellite, I think in the order of 0.5 meters. But I'm not exactly sure because that was data we received.
Yeah, thanks for that, Alex. Just a follow-up question. I've lost it here. When you were looking at the Bribie Island area, was there any long-term simulation done on the resiltation of the dredge channel and maintenance dredging?
So we didn't necessarily look at maintenance dredging. So our methodology was to basically punch in the dredge channel and to see what would happen in the time frame of 6 months. And then this would inform how we consider if maintenance dredging is necessary in the first case. So we just did that one set of simulations that kind of told us, they kind of gave us an answer on whether we would actually have to do maintenance dredging to keep the channel working.
Yeah, cool. Thanks for that, Alex. Mark, there was a question regarding the downstream sea level boundary during and after rainfall. What did you and the team use for that downstream boundary?
Well, we took the downstream boundary quite far offshore so as not to be influenced by local river flow influences. And that just came straight out of tidal charts, I guess, high tide, low tide levels. When we looked at future climate scenarios, we obviously adjusted that for those. Yeah, I'm not sure if that answers the question. We didn't have the boundary being influenced by rainfall though. It was more just a sea level driven boundary level.
That's all good. Thank you for that. There was a question about whether you, Mark, looked at and the team looked at more recent or more frequent events such as a 10% AP or 1 in 10 year ARI, and if you didn't look at those, was there a reason why you did not?
Yeah, so we actually looked at a very wide range of different events covering very extreme events, so more severe than the 1% event, just to make sure that we had some idea what was going on, all the way through to mean annual low flow type events, to understand the different effects that it may have. The only reason I've focused on the 1% event in the presentation was that was the condition of consent relating to flooding the Opotiki town. We certainly looked at a very wide range of events to understand the likely behaviour of the new mouth and how that should be factored into design and maintenance dredging considerations and the like. So we did cover a very wide range of different events in the model simulations.
Cool. This one's for Alex first, and then I'll throw the same question to Mark. Alex, can you give a bit more information on the sort of applicability of the model, so what sort of time frames is it possible to run these things over, weeks or months, and also the spatial scale of what you were doing?
Mm-hmm. So, well, the time frames for this kind of model are in the orders of months. Getting into years will be difficult because, it was quite a detailed model, and you could do it if you have enough time, but typically you'd say timeframes of months. Spatial scales, like we were using 20-meter cells to get the area of detail that we needed. You can ramp it up and look at coastlines from a more broad scale perspective. So hopefully that answers that question a little bit.
Yeah, that was good. Mark, yeah, sorry, mate, you go.
Yeah. My go at it is typically running the 1% events. We were looking at about a 60-hour simulation time. Now the simulation speed is dependent on the number of wet cells in the model at the time, amongst other things. So when we were running the more severe events, when there was more out-of-bank flooding, it took longer than running the less severe events when everything was contained in bank. But typically about an hour or two of simulation time to run the 60-hour event. We would generally queue them up overnight and batch them up so that we'd run a whole bundle overnight and have a look the next morning. But runtime for what we were looking at initially, it was taking a bit longer, but we made some refinements, and runtime didn't turn out to be an impediment to us. We generally had results the next day to questions that we had asked.
Yeah, thank you, Mark. Alex, did you have a feeling for how long, in real world time it was taking to run your model?
Yeah, definitely longer than overnight. So for those 6-month simulations, it might be in the order of a few days. I can't remember exactly, but it might have been about 3 days. So you had to be quite patient and make sure you get it right before you set it off.
Yep, no, that's great. Mark, I've got a question from Mohammed. He said, yeah, thanks for the interesting presentation. And he wanted to know why a gate hadn't been used at the existing river mouth to control or pass flooding, and potentially if a gate was used, could it be a geopolymer or a floating gate that could increase the flow of floodwater during peak periods?
Well, one of the things we were really keen to do is to maximize the scour potential of the normal tidal prism through the training walls. Our analyses indicated that maintenance dredging would be required. So the more flow we could pass through the training walls every tide cycle, the less maintenance dredging. So we're quite keen not to keep two mouths open. For that reason, we wanted to focus as much of the day-to-day flow through the new mouth, through the training walls. The other reason we didn't consider a gate, I guess, would be cost and know-how and durability in that environment. I don't know that much about that sort of thing. That would have been a decision made by some of our more experienced design engineers. My expertise basically just covers the modelling. So I certainly know we were trying to concentrate as much of the tidal flow through the training walls as we could, though, for that reason.
Yeah, thank you, Mark. I'll throw this out to the floor because it's relevant to both models. But Anon has asked, would it be possible to consider the future climate change into the model? So if one of you wants to jump in.
I'll jump in there. We did consider, when we say future climate change, for the work that I was doing, there are really two elements to that, where the floods are predicted to get more severe, so higher peaks, and the sea level is expected to get higher as well. We certainly considered both of those effects in our modelling assessment and how things would change as the climate changes, but I don't think we considered any other factors to do with let's say to do with the inflow, the suspended sediment, or anything. We didn't change anything along those lines as far as the climate change went. We just considered those two factors.
Thanks, Mark. I'm sorry for pumping you with lots of questions. We had Ali. He was asking how many locations did you collect the sediment data for modelling? And I guess Alex, after Mark's had a go, if that's relevant, if you could also answer that.
I can't actually remember the number. I've got in mind the number 70. It's of that order of sediment samples. Maybe not quite that many, maybe 50 or so, but a number of tens of locations.
To save Alex, I suppose that the question really depends on how homogeneous your sediment is at your site. Like if you're on a beach and you have one type of sand, you can go and pick a couple of different locations and be reasonably confident that you've captured the distribution. Whereas in a river, like what Mark was looking at from the presentation, there was really large spatial variation as you went from the upper part of the river, where it was very gravelly, down into the silts and the sands and the fine material. And that's not only spatially when you're looking down on the map, but also if you were to dig a hole under the bed, you might find that there's coarser material at the surface, which has got subsurface material below that. I don't know if you had anything to add to that, Alex, or...
I think you've summarised it pretty well. Yeah, we could consider it here as just one homogeneous material. Yeah.
There was a question that's been upvoted a number of times, and that's can these types of models look at different sediment fractions? any sediment transport model is going to be able to look at the distribution of sediment. So in the real world, you've got silts, and then on the bank of the river or the beach, you might have some sand, and then in areas where you've got really fast flowing water, you might have gravels and things like that. So you can vary the spatial distribution by telling the models where the sand or the different fractions should go, but also discretizing up how the fractions might move, whether they're suspended, so just moving through the water column, whether they move as suspended and as bed load, or if they're like gravels and coarser material just moving as bed load only. So another question for Alex. It sounds like dredging would be expensive and ineffective. What other options are they looking at, if any?
Yep. So, well, I think we agree. Dredging is expensive here. I don't know if you remember from the recap in that last picture, but just at the end of our project, naturally that shoal started to break through. And at this point, it looks like that channel might be semi-stable, like it'll be continually getting shallower. It might move left or right a little bit. It might get deeper during certain periods. But for now, I think that the access issue is enough. You can be put away for a little while. So I guess it's a bit of a wait and see. Like, it's such a dynamic area, and where it evolves to from here, like, I mean, we're not exactly sure. So while access is available right now, I think the community is a bit happier. So
thanks, Alex. There's been a couple of questions come in about whether the models can predict bank line or bank erosion. So we're not talking about scour of the bed of the river. We're talking about when you get helicoidal currents and scour of the outside of a riverbank, and that moves laterally. So there are models that can do this. The question around Tuflo specifically is that it has some allowance for bank erosion, but it's it doesn't really do the full morphological lateral movement that you might see in like a very large meandering river system. All right, so that was good. So the question came, Mark, was there an increase in the efficiency of the entrance, and did that result in more oceanic flooding, I suppose, by opening up that entrance?
The existing entrance was quite heavily tidally controlled as well. The peak flood levels attained. In terms of oceanic flooding, there would have been a small effect. When we were looking at, I mentioned the joint probability assessment, we looked at 1% flood in one of the rivers, a 5% in the other, and a 5% oceanic, and then we shuffled them around. So if we had a 1% oceanic event and the 5% and 5% in the rivers, when we came up with the maximum flood level attained for a 1% event, it was any one of those combinations, those permutations. So we kind of did a maximum of the maxima. So for each time we answered the question of have we increased the 1% level, we looked at that three-way joint probability equation and satisfied ourselves that we weren't. So it was implicitly taken into account in that analysis in demonstrating the 1% event compliance. It wasn't just a 1% flood. One of the permutations considered was a 1% oceanic event with less severe river floods. So we did take it into account.
Yeah, thanks for that, Mark. So we'll hang around for another 5 minutes or so answering your questions. I had a good one here from Anon. Alex, I'll throw it over to you. What are the common methods for morphological modelling, calibration and validation based on your experiences?
So, well, what we did that I didn't really show today is that we looked at it in a quantitative manner. So we selected key areas that we wanted to focus on. So if you remember from the presentation, that's Bribie Bar and Caloundra Bar. They're the areas we wanted to get right in the model. And we basically looked at metrics such as common ones like root mean square error, mean absolute error, some correlation, and also another metric called Brier skill score, which itself is a useful metric because it has terms that make it up that relate to things such as phase error, amplitude error, and a bias error. So we basically had a whole suite of metrics to guide us in whether we're doing a better job with this model test than we were with our other model test. Because just looking at figures qualitatively, it can be quite subjective. So that's probably that's how we did it, and that's probably one of the main ways of doing it, like just the quantitative test. But I mean, it's also important to look at things visually and make sure that you're certainly checking, getting the right responses in the model.
Thank you, Alex. I've got a follow-up question for you. After this assessment that you've done on Bribie, do you know if there's going to be any further assessments looking at the effect of extreme waves or inundation risk to that area on the inside of Bribie Island?
Yeah, there will be, but not from the same client, and it's not necessarily a project that we're doing right now. But I mean, the breakthrough has had implications for the town there, and for basically all like the esplanade around there. So with larger water levels and now increased wave penetration, I'm sure at some point there will be additional inundation modelling done.
Yeah, so in terms of your interpretation of like the risk there, if there was another big event with really big waves and like a storm tide through there, do you have a feeling for what might occur in that region?
It's certainly going to be larger. So, I mean, previously the tide signal itself was so attenuated, and storms, and the same would go for like a storm surge coming in. So, inundation risk is now higher post breakthrough. So that's why I think there would be at some point some additional inundation modelling. Not sure when.
Yeah, thanks, Alex. It was sort of more of a comment here from Denver. Knowing the amount and volume of sediments, how can this be used to manage and minimise the need for dredging? So I can answer this one. So if you have an understanding or an estimate of the likely sedimentation rates, over 12 months or even the next few months, it gives you an idea of how much and when you might need to have a dredge campaign to occur. Where this kind of modelling can really help, though, is if you've got an existing sedimentation issue and you're looking at different options. So trying to say, okay, if I design this breakwater or I design this shape of structure, is that going to be more efficient from a cost perspective, but also from an environmental perspective, moving forward? And it can help you to choose which option to go with. Cool. So I might have one last question here. If we missed out today on your questions, we'll basically go through and answer all those and send them out when there's a copy of your certificates and the webinar goes up on YouTube. From Owen, Alex, do you think it's possible that the northern section of Pumice-Stone Passage may become basically like an icol in the long term?
It's possible. Yeah, so the Caloundra Bar, as you can see, was closing up, and that bar height's probably only going to reach a height of around the highest astronomical tide. So it's not really a strong mechanism to make it build up a whole lot longer, a whole lot higher. And so, I mean, it's certainly possible that during a decent storm event that these coastal berms could open again, like not dissimilar to an icol. So it is possible, yeah.
Very good. All right. Well, thanks very much for all your questions and thanks for great presentations. Tegan mentioned one of the webinars earlier, but if you go onto the AWS website and look at sediment transport, there's some really good stuff from Cray on the 1D evolution. There's geomorphological webinars you can check out. There's recent coastal webinars as well, and there's a whole range of other flooding stuff. It's a great resource, so please jump in and take a look. Thanks, Tegan.
Thank you, Mitch, and thank you again to Alex and Mark today for your efforts preparing these presentations and sharing your wealth of knowledge, and to Mitch and Ian for fielding the questions. So it's been really informative for our attendees. I'm sure our audience have found these case studies really interesting and valuable, so thank you again. So before we close off today, just a few housekeeping reminders. So the recording of this session will be made available and live attendees will be emailed a certificate of attendance, which is great for collecting your CPD hours. Please also take a minute to fill out the feedback survey for the AWS that'll pop up. So that's really important for guiding their future content. There are a number of AWS webinars and live courses coming up. So please go to the AWS website. So that's www.awschool.com.au. and register for those if you're interested in them. Alrighty, so thank you again for your attendance today, everyone, and we'll see you again next time. Thank you.